Okay, so here we go. A total of 23 Gosset High School students admitted to State University, and some of them were offered athletic scholarships. So the guidance counselor looked at their composite scores shown in the tables and said, does it seem that State U might admit people with lower scores if they're also athletes? And of course, school guidance counselors have to do a lot of stats in their work. So we've got two different lists here. I'm trying to do this where I feel comfortable with it. So we've got two different lists. So we put them with mine. I put them, whoops, I want to go here. With mine, they're in L2 and L3, and there are 16 names in L2, numbers in L2, but there's only 7 here in L3. So we've got all these numbers. And so we're deciding, do these people really get an advantage? So it asks, it says test an appropriate hypothesis. Well, that means we're doing a hypothesis test and state our conclusion. So I'm dividing these into subscript N and subscript A, non-athletes and athletes. I do a calculation of both. I find that the mean of the non-athletes is a score of 24.75 with a standard deviation of 2.84. Notice I put the N's here, 16 students. And then on the 7 students that are athletes, their mean was 2.186 with a standard deviation of 3.29. Interesting. Larger sample size, smaller standard deviation, small sample, large standard deviation. Remember that. And so the other things I put here, I went ahead and put alpha here. My degrees of freedom are 10.13. I'm going to find those in a moment. But here we go. Our null hypothesis is that the mu of n, this is always a population variable, parameter, mu of n equals mu of a. And the alternative hypothesis is that mu of n is greater than mu of a. And again, the calculator is going to find this for me in a minute. And I'll be honest, I ran the test to get these numbers as well, but I filled them in. I ran the test, filled them in, and then went from there. So here are our conditions. It's not random, but this sample should be representative of all non-athletes and athletes, especially from this high school that are going to State U. 16 is less than 10% of all non-athletes admitted. 7 is less than 10% of all athletes admitted. So there's my 10% condition. Non-athletes, I drew the model. My windows, I did these by 4s, both of them. And I went even numbers on bottom and top and then put this in there so that it makes sense. If your graph doesn't look exactly like this, it doesn't matter. But as long as I can get something that I sketch on here, again, I went by units of 4. You could have gone by units of 2. 3 didn't give me that well, but 2 gave me something okay. This is huge if you go by 2. There's a lot of bars to draw, which is fine. So those are both roughly symmetric and unimodal. So I can do a 2-sample t-test. So far, so good. So here are my calculations. I said that t is the mean of my first sample minus the mean of my second sample. That should have been that in, sorry. Minus 0, which is what we consider the difference here, divided by the standard error. This is on your formula page, and that equals 2.02. And then I wrote standard error down here, how I find standard error. I want to make sure I put that in there. The standard error of this squared over n plus this squared over n, the sum of those, because remember with standard deviations we can't add them, but we square add in square root. So then I ran my test and I said the probability of my alternative hypothesis occurring, mu of n greater than mu of a, equals the probability that t of a degrees of freedom 10.13 is greater than 2.02, which was my t-value here, found by the calculator, not my calculations. I ran the test. Okay, let me put that back on here. So stat test, it's a 2-sample t-test, so that's just simply number 4. And then there my list, it's a greater than, I'm not worried about pulling it, there's my calculations. 2.02, the probability of that occurring is 0.035. And then it's got all my numbers that I used earlier. So with a low p-value compared to alpha, remember I wrote alpha over here, we reject the null. There is some evidence that state you might admit people with lower scores if they are also athletes. There is some evidence. It's not strong evidence. There's only 1 0 there. This is really close, ladies and guys. Most of you understand. That's really close to 0.05. Not 0.5, but 0.05. And then it asks, hey, can you run a confidence interval for that? Sure. So I ran the confidence interval. The conditions are met above. Boy, my writing is sloppy, isn't it? So my confidence interval is the difference of the two means, plus or minus t star of 10 times the standard error. Okay, 10 degrees of freedom. You could have put 10.13. I just wrote 10. And that value is 0.302 and 5.48. Okay, now something I didn't write down, and I'm going to show you, remind you how to do it here. So we're doing a 90% confidence interval, and my degrees of freedom are 10. So I'll go on here. Degrees of freedom are 10. Okay, 90% confidence interval is this column, which is a 0.05 on each side. So that number, T star is 1.812. I should have written that up here, or here would be 5. T star of 10 equals 1.812. Okay. So there's my interval, 0.302 to 5.48. We are 90% confident that non-athletes average between 0.302 and 5.48 points higher than athletes on the ACT. Okay, I hope you're comfortable with that. And with that being said, shrink my screen and call it a day. Hope your day goes well.